Okay.
Okay, it must be recording to the cloud because I don't have any other option, so it must be recording. Okay.
But for some reasons, I cannot record, you know?
Yeah, I understand. I don't know why that might be, because I think you are the host. Yeah,
I
you
am
are
the host, but I don't know really what is happening, because today morning I could record and I did record. Then I don't know. I stopped recording for a break and then it was never possible again.
Okay, but now it's recording and I'm at the lab.
So I think you can start. I'm go off and the time is yours. Okay,
welcome everyone. So it's me, Sebastiao. So let's turn the camera to me. If I Okay, hello everyone. So I'm in the NMR lab in our research group here. I belong to the condensed matter physics department, group in the physics department. I work in the research center called Center for Material Science for Complex Fluids and Materials, Advanced Materials. And we are right now in the NMR lab. So let me show you. So we have different NMR setups coming down from the frequency. We have a 300 megahertz Bruker superconductor with NMR Advanced 2 console. And we see here Thomas Zilski, which is visiting us and is operating the NMR console. Actually, he will show us some of the measurements and some adjustments that we will be making here on the machine.
Hi, Thomas.
So this is the Bruker console that operates with this superconductor. But we have also one electromagnet, which is this big gray thing here. Right? So these are two cylinders that contain two coils. So this is a kind of Helmholtz coil setup. These two coils have an big iron coil, and all this unit can weigh about 2 tons. This is a conventional electromagnet or conventional magnet for NMR. Actually, it was designed for EPR, but we asked Bruker to adapt it for our own purposes, which is NMR. And then we have our own field cycling equipment. Oh, by the way, just let me introduce you to Roxana. She's visiting us as well. So we'll see it. You can put the sample inside. Okay, so our probe head can accept samples in NMR tubes, which can be this standard 5 millimeter NMR tube, or can be wider because it has a wide bore, let's say. So the sample is placed in the probe head, which is at the end of this probe arm, and it is placed in the middle of the magnetic field that comes from left to right or right to left. I don't know exactly in which side is the north pole. And this probe arm then is connected by a coaxial cable to the preamplifier, which is this unit here standing on the floor, which then connects to an NMR console. We have other NMR consoles that can operate with this equipment. For instance, this is a Magritech, which is now being prepared to operate with a different setup, and it is not running right now. But I was explaining you that we have our own field cycling equipment that we developed in-house. And unfortunately, I will not be able to show it running today, but I can show you that it has this small iron core magnet, but in spite of being made with, in spite of containing iron, is nevertheless possible to make fast field cycling with it. This was the first generation. It has about 15 years now, and this is the new generation, which we are now trying to put in place. We have this handle because we are supposed to be able to carry this small unit as a, let's say, a portable fast field cycling apparatus. This small magnet requires a not very large power supply because it operates with about 5 amps maximum current. This is the power supply that has to deal with the switching of the magnetic field, like you have heard today, this morning. So we have 2 units because we are making 2 units in parallel. This field cycling equipment will run with the Magnitech console, and we are working on the software that will control the machine. The reason why I will not be able to show it because the software, it is at the initial stage, and I cannot immediately show it to you. Okay, so coming back to the measurements we do here. I can show you a profile, which you might have seen plenty. I showed some of them myself the last week. And so if I can show you here some data obtained by Maria Beira, a previous PhD student of mine, we have here a frequency range that extends from the 10 kilohertz to almost 1 gigahertz. This is about 500 megahertz, or 2, 3, 4, 500 megahertz, and see the profile of some compound. And let's say I will cover here this frequency range between my 2 fingers is the frequency range that we can have access with our standard equipment. So this will be the 300 megahertz point that we obtain with the superconductor. This frequency range is between 10 kilohertz and 100 megahertz is obtained with our electromagnet, and the remaining frequencies are obtained with field cycling. Actually, you can see here why field cycling is so appealing, because with a single machine, we are able to cover several decades of frequencies and help us to produce this rather complete dispersion profile. So, Roxana and Thomas, they came and they are now making measurements in this high frequency range where they use this 300 megahertz superconductor and the electromagnet. This electromagnet requires cooling, and there is water circulating inside those discs over there, and this is the cooling unit that circulates the water. Being an electromagnet, and contrary to the superconductor, we need to control the current, and we can adjust the current, and this is the purpose of this unit, which is a power supply where we can control the current. We can make a calibration. Actually, the calibration was provided to some extent by Bruker, which is the company that made the equipment, and it can tell us for which current should we put in the magnet to obtain a given magnetic field. Right now, Thomas, you are operating at which frequency? 11.7. So for this current, we need 6.8 amps on this big electromagnet. So when Thomas arrived, just 1 second, Thomas. When Thomas and Roxana arrived, we measured at 90 megahertz. So at that moment, the current here was about 60 64 amps, so 10 times more current was circulating in the magnet. Okay, so one thing that you must know, or you will probably know by now, if you watched all the sessions previously, we need to establish a resonance situation between the energy levels of our spin system that give us, that is, let's say, that is given by the Larmor frequency that depends on the element, the nuclei, the spin, the nuclear spin that you are considering. Here is, we can think on hydrogen, so we have a two-level system, and for a given magnetic field, we have a certain resonance frequency. Here right now, the resonance frequency will be 11 megahertz. So in the NMR console, Thomas set the frequency to 11.7. So we expect to obtain resonance at 11.7. And to check if we have resonance, we have now to adjust the magnetic field properly in order to have a well-resolved signal. And that's what Thomas is going to do right now. He's adjusting the current slowly with this how to say, is a potentiometer, is a button that have many turns. And here you see the effect. Let me try to approach the screen. Okay, so by changing the current slowly, we are able to get to the point where this signal that is waving is completely resolved and no waving or almost no wavings are observed. And then when no waves are observed, we finally get to the situation where we have resonance. And resonance here in this case means that our magnetic field corresponds to a Larmor frequency that is equal to 11.7, which is the frequency set in our spectrometer. And our spectrometer is sending radio frequency pulses to the system exactly at this frequency. You can change to spectra perhaps. So we can have the signal in time, but we can observe the Fourier transform of that signal, and we get a line, which can be, the width of the line obviously depends. You can expand a little bit. The width of the line is related with the homogeneity of the field, and in case of this electromagnet, the homogeneity is not very high. Therefore, the width of the line is not so small. So, yeah. Okay. So the software here that we use in this particular case is Bruker TopSpin, not the most recent version. And what we can do is to change the pulse sequence. I suppose you saw in this morning this being also these settings also being made in the stellar machine when you choose between polarized or non-polarized field cycling sequences, and depending on that you mix or not this inversion recover method together with field cycling. But here in this case, we use solely either the inversion recovery or saturation recovery in some cases. So one thing that we have to set is the type of pulse sequence, which is here inversion recovery. I don't know if someone told you already, but I suppose someone must have told you. The inversion recovery pulse sequence actually is here described. Sorry, Thomas. Is here described by a sequence where you have a pulse with a certain width and a certain amplitude, followed by some tau, which might depend, is our so-called tau that will be part of a list. And then finally, a measuring pulse, which is called the 90-degree pulse. And after that, we get the free induction decay in our detection system. So this is the 180 pulse or pi pulse, a tau, and half pi or a 90-degree pulse. And then we make the measurement and get the FID. So this is the pulse sequence. So, Thomas, what next? What do we need now? We need.
We have a list of taus.
Okay, so we need a list of taus. You saw probably with the stellar equipment that we have also to select either the number of taus or establish a list between the minimum value and the maximum value. Here is the same. We just select the list in this particular way, and after that,
Have to check
the WOP. Maybe we
where's the
should
WOP?
try.
Yeah.
Okay. One thing that eventually, I don't know if it's stellar machine we do that, or I'm sure it's possible to do it, and I'm sure it must be done at some point. Which is the tuning and matching of the probe head in your transmitter and receiver. So here in this particular case, what we are looking for is a minimum of the impedance of the circuit, or a good match between the impedance of your probe head with that of the transmitter. So we look for a minimum, and this minimum must be established, or the good conditions must correspond to our target frequency, which here is now 11.7 megahertz. And how do we do that? I mean, to do that is pretty much the same as tuning your radio to a given radio station. You just have to adjust a capacitor, which here is represented by a button that we be rotating. And I don't know if you are able to see, because I'm not sure if I'm able to change my camera, or maybe Thomas, you okay.
You go
No.
there.
Okay, yeah, that's good. So you rotate the button and we see the effect. Dramatic. Okay, so by rotating, I think you see by rotating or changing the value of the capacity, we are changing the resonance conditions of the probe head, and we have to put these resonance conditions exactly in the frequency that we want. So this is tuning and matching the system for the frequency that we need to have. I suppose that to some extent in the stellar machine or in any other equipment, you have to do the same thing. Okay, so next, Thomas, okay, so we stop this tuning and matching.
Have to check the pulses.
We have to check also the pulses. Okay, so this is an important thing. Maybe GS,
Maybe GS.
yes, maybe GS.
Yeah.
With the plus with ZG. Okay, so we have one more step in this setting of the experiment, which is the proper adjustment of the pulse width and strength that we have to use in our pulses. How do we do that? Okay, Danuta, did anyone explain the concept of the rotating frame and the effect of the 90-degree and 100-degree pulse sequence or not?
I think nobody explained.
Oh, okay.
I mean the pulses, yes, somehow, but they were only mentioned like something which is obvious, and it definitely is not. So if you could say something, would be great.
Okay, so I will not show it with mathematics, but I will show it based on the effect that it produces. Okay, let us sit down. Thomas, can you sit down as well? Okay, so I'm sitting and Thomas is helping me at the console. So, okay, so we have now a single radio frequency pulse applied to our sample. And we can look at the signal as a function of time. So for a moment, this is time domain NMR. Okay, so I have to tell you that I don't particularly like, or it's not a question of like or dislike, but speaking about time domain NMR or spectroscopy NMR, for me, is a kind of speaking about the same thing, but choosing different words, because it's all the same. Except the difference is that what we do with the signal we detect and what are the conditions of our experiment. So, okay, if we look at the signal alone from the point of view of the FID, depending on the time, we have a signal that is the free induction decay evolving on time. But if I now make a Fourier transform, I will be in the conditions where I could say that I'm ready to do some spectroscopy measurement. In this particular case, is of no good because the frequency is very low, the resolution is not enough for us to really perform, modern spectroscopy measurements. But still, it's the same thing. So we have a signal, and I'm looking at the Fourier transform of the FID. And now what we have to do? We have to make sure that our pulse is enough to do two things. One is to bring the magnetization to a situation where we can detect a signal. This is usually referred as a 90-degree pulse. Maybe later I will show you a draw, but maybe this is, if we imagine my finger is pointing vertically, so the magnetic field is pointing upwards, and my magnetization starts by being aligned with the field, applying a 90-degree pulse should produce an effect that the magnetization is turned by 90 degrees, so to a plane perpendicular to the vertical axis, and being on this plane, the magnetization becomes detectable. So the detection system detects components of our magnetization, which is in the plane perpendicular to the vertical axis. So having a 90-degree pulse means rotating the magnetization to the plane perpendicular to the initial situation. And in that situation, we are able to detect the signal. And this is the Fourier transform of that signal. So if we rotate the magnetization by less than 90 degrees, we still have some components that we can, project on the plane. So we detect the signal, but the intensity will not be the maximum, because if I rotate, for instance, 45 degrees, the projection of this vector on the plane is less than the amplitude of the full magnetization. So the maximum amplitude detected is obtained when the magnetization is rotated by a full 90 degrees angle. If we rotate more, we can even get to a situation where magnetization rotates from the vertical to a vertical, but pointing downwards. And then no component is in the plane, which means there is no detection. So we can use this fact to adjust properly the 90-degree pulse. We will change the pulse width continuously until we get to a situation that we don't detect any magnetization. Let's try. So Thomas is increasing the pulse width, 3 microseconds now, 4, For now, the magnetization right now, the spectra increased the maximum. Thomas just decreased the screen. So 5, 6, and 7, and it starts to decrease. So somehow the magnetization reached the maximum, and now I'm applying pulses that force the magnetization to rotate more, so I detect less signal on the plane. And finally, by the time we reach 8 microseconds, our signal is almost, if we take the average of this, is basically 0. So at 8 microseconds, we rotated the magnetization by 180 degrees, which means that half of this value, 4 microseconds, will give us the maximum amplitude that we can get. So we now have our 90-degree pulse well established, or let's say as good as we are happy to right now. Okay, so what's next? To measure T1 using the inversion recovery pulse sequence on this machine. So we change the pulse sequence to the pulse sequence which has the inversion recovery technique. We check the pulses to be sure that we have the proper width. And P2, we have 2 pulses, one which is as the double of the width of the other one, so 8 microseconds. And now we set the repetition time, which means the time that we leave the system to relax back to equilibrium. So again, I rotate the magnetization by 90 degrees, and then if I don't apply any more power or any more pulses, the magnetization will go around, will process and go back to the initial state, which was vertical. And this takes time. This actually takes a time which is larger than 5 times the relaxation rate or the relaxation time, the spin lattice relaxation time that we want to measure. So we need to set here a repetition time which is at least 5 times the value of the T1 that we expect to measure. So 1.3 seconds in this case.
We are ready.
Okay, so we are ready, and we set TG, which is 0 go, and the acquisition will start. Okay. In this particular system, we don't have, the concept of blocks. I will show them in a moment. But we have the possibility to observe step by step. We make several scans, and during these scans, we see this increasing. But this is because I'm just adding values to make an average and to reduce the uncertainty. And we are repeating this process by different taus. So we have 16 taus, and we are on the second one. And for each tau, we make 8 scans. So we accumulate 8 times the FID. And after that, we make an average, and that will be our final FID for any given tau. So if you have been paying attention, or if you will see that this line in the spectra, after accumulating 8 times, has been decreasing from the initial value. And at some point, this amplitude will be almost 0, okay? We have to be patient. This experiment will take us about 3 minutes. What sample is this, Thomas?
Water with gadolinium.
So this is a sample which contains water and gadolinium. Okay, so it should be considered, let's say, paramagnetic solution, which we expect to have some paramagnetic relaxation enhancement due to the gadolinium. So the T1 that we will expect to have is not that of water, so it will be shorter than water, right? Okay. So you see now that by the time we got to the middle of our list of taus, we are now at tau number 8, now 9. The spectra that initially was negative now is positive. So we are coming from the inversion state to the recover state. Okay. Meanwhile, I can show you here, not very nice, but this is in the stellar machine. These are the slots, the blocks of, I don't know, it's blocks. What's in stellar machine? The name for that? Blocks, I think. Anyway, this is the FID for each tau. Okay. Okay, so we have 1 more minute to go. We are at tau number 11. If you have questions somewhere out there, someone out there can ask. Meanwhile, we have 1 minute, so we have time to check if you want. We are expecting here. Roxana is just watching the presentation. Okay, let me show while we wait. Let me show here the console. It's pretty much standard for all machines, all equipment. It must have equivalent circuits like this. These are standard things. So this is the pulse sequence and the computer that runs the acquisition, the multiplexing, the detection, etc. And then we have things that control the probe heads and the tuning and matching. And here are the amplifiers. And in this case, in this machine, we have several amplifiers. One of them has an output of 1000 watts. So this machine is for solid state NMR, or can work for solid state NMR. There's another output which is 300 watts. And then we have 2 extra for 100 watts, specific for liquid. So we have these 3 amplifiers. We don't have any gradient unit which we could use for imaging. That's or diffusion. That's the you know, the business of Thomas, diffusion, the imaging and diffusion. Okay, so meanwhile, this finished. So how does it work here for our T1 measurement? So we have 16 FIDs, and from the FIDs we could, do you mind if I just borrow your just borrow the mouse?
Sorry.
Okay, no, finish that. I will just explain, but just before that. Okay, so we can have an FID, right? The FID as the detection of this signal is as in stellar is a quadrature detection, which means basically that we have either 2 detection circuits, or we are able to make a demodulation of the signal, so the detection of our signal in a so-called quadrature. Well, it's basically, it's not important to go into details right now, but basically what we need to measure T1 is to measure the amplitude of the FID right when it starts. In order to make their measurement in a precise way, we need to have a proper adjustment of the phase of our signal. Most of the time, this is achieved working not with the real and imaginary part of your FID, but working with the modulus of these two signals. And working with the modulus, we avoid the problem of the phase adjustment. One other way to do it, instead of obtaining the initial value of the FID, which is here, at the initial point of the FID is here in this case, we can work with the spectra. And this is what Thomas was doing. He was showing us, now I don't know, I think it was here. Okay, he was showing us the spectra, and he was trying to adjust the phase in order that this spectra is really negative to correspond to the magnetization that we got for the initial tau. Can you repeat? Can you move up and down? So Thomas is just moving around, and by moving the mouse, is able to adjust the phase that we see here in the form of the line of the spectra changes its shape, because we are going from the real. This is, by the way, this is the real part. Actually, the negative is negative in this case, but can be positive. Now it's positive. And this is real part. And the imaginary part, it would have it like this. This will be more or less the imaginary part, which can be also positive and negative. So, but now we want the negative part. Okay, so the spectrum now has a nice, proper phase adjustment. And now we go to the situation where all the 16 FIDs will be processed. So FFT will be applied. So we will get 16 spectra. And now we have to select or to calculate the area below the area of each spectra, right? So we select the spectra and we define the window to calculate the area. Okay. So we define the window. So all the spectra will be integrated, and this window is the window that will be used for all of them. And now we will get the relaxation point. So all these points were obtained by integrating the spectra, each one of them, and they produce this series of points that define nicely an exponential recovery. So the magnetization starts by being negative and the smallest possible, according to our list of taus, and recovers to the equilibrium value at the end of our for our last tau. And now we finish by making a fit to obtain our relaxation time. We can observe in a linear scale or in a logarithmic scale, which I prefer because we can notice more easily any deviations, systematic deviations that can be the announcement or an indication or of a possible bi-exponential fit. How can we say that we need a bi-exponential fit, or when we need an exponential fit or not? Well, one practical way is to observe how the points are around our fitting curve. If they are randomly distributed, as it is reasonably well in this case, we say there are no evidences of requiring a bi-exponential decay. But sometimes we have points, a succession of points which are above the line, and in another area we have points that are below the fitting curve, and that's an indication that we need by exponential decay. So what's next?
Take data to KITER.
We take data to a program that can show us how the T1 values look like. Okay, you can export those magnetization decays. You can export that data and put in Fiteo or some other program, and then you can fit it elsewhere. You don't need to stay in the Bruker console to calculate the T1. You can do it as well here. Thomas is doing that, so we just collect the data and copy, and then paste here, and then make some additional calculations, and finally fit the magnetization decay. Okay, so that's the fitting curve, and here somewhere is the value. Of course, this value should be the same value that Bruker was giving, so there is no differences there. Okay, within decimals is about the same. Okay, so finally this point goes together with the additional points, and I think Thomas is willing to show how the points that he has been obtaining this week, the past week, how they put together, how they look like. So there is here some evidence that what might be the paramagnetic relaxation enhancement that he might have in this sample. So what's next? Measure at low frequencies in the realm of fast field cycle to complete this question. Okay, so thank you very much, Thomas. Thank you, Roxana, and thank you all for watching.
Thank you. Hi, Roxana. Thank you, the whole team. There are questions. Pedro, Adriana from my group is asking, do you need the deuterated solvent in this experiment?
Do you need to?
Deuterated solvent in your
No, we don't need. I mean, well, we could use, okay, let's put it this way. We can use deuterated samples, or we can measure using deuterium, of course, but we don't need to have any lock. And usually, or sometimes, deuterium is used to produce, to be able for the spectrometer to lock on the frequency of deuterium, for instance, and to to automatically correct itself and keep in resonance during the full time of your experiment. But here, because we are interested in the area of the spectre, or in other words, in the initial amplitude of your FID, any shifts out of resonance do not matter within a reasonable range of oscillation. So we don't need lock in this particular case.
Okay. I hope, Adriana, you are happy with the explanation. And do we have more questions? Faisal says that the lab is wonderfully equipped. Fully equipped.
Sorry?
Your lab is fully equipped. This is the comment.
Okay, so you see, let me show again. The opinions diverge. Okay, let's put it away. This, what you see, is likely to be the same in everyone that works more in physics and NMR. So cables all around, screws, and things, because we are always trying to modify and change things. Probably if you go to Roxana laboratory or to Thomas laboratory in Poznan, you will see a much nicer thing, not so many things around and so much equipment lying around, etc. Because here we are always modifying something, or there is always someone making some modification.
And it should be like that.
So, more questions or comments?
There is a question.
Yes.
It was a great explanation, especially about pulses. Okay. It was great to see this FID in Fourier transform representation for better understanding what is going on during experiments. So this is a kind of comment.
You can and you should, if you are the colleague or the person that made the comment, if he has the chance to simulate the data in a computer, he will find interesting to generate a signal that depends on time and make the Fourier transform and play with those functions to observe the same thing in a numerical way without requiring the equipment, that it can be easily performed if you play with a sinus or a cosinus, so an harmonic function multiplied by an exponential, and you just apply Fourier transform, you will be able to see exactly the type of line that Thomas was showing us now on the console.
There's one more question. In your experiment was inversion recovery. Okay, do you apply saturation recovery, which takes less experimental time? I mean, it's faster.
Yeah, it's a good point. Thomas was suggesting the same thing. Well, if it's a question of time, certainly for experiments that involve water or some other
long relaxation time, yeah.
With long relaxation times, definitely having a way around that, another alternative to inversion recovery is nice. To be honest, in most cases, I personally don't use saturation recovery. I use inversion recovery.
Thanks. Do we have more questions? I do not see more questions. So Pedro, thank you. Thomas, thank you. Roxana, thank you. Thank you, thank you, thank you. And I would have a kind of idea now, because in principle, we're supposed to finish in half of hour, so 3:30, and then have a break. However, I would propose to have now half of hour break, and then we'll start with next example of fast recycling measurements, which Elizabeth from my group will show, if this is okay with you. Because if we start now, we'll be tired and so on, and for half of hour, it does not make sense to start. So if this is okay with you, I'm just writing, we start again at, yeah, in half of hour.
Okay, bye-bye from Lisbon.
Thank you. And you know, this I do not touch this recording because I know it will end bad.
Okay, do you want me to stop or pause?
No, let it go.
Okay, then.
I know that if I stop it, it disappears.
Do not worry. I will be here because I will be working with Thomas, so I can start recording in half an hour. Do not worry.
Okay, thanks.
Bye-bye.
Bye.